Okay, so today it's much more people than it was last time, and therefore, in order for them not to be completely disoriented, I repeat a bit what we did before. So I started this business of random matrix theory with the symmetry, because the symmetry is actually for classical random matrices, it is all what matters. Since this matrix is a full matrix, it corresponds to so-called zero-dimensional system, therefore there is no space, and therefore the only thing that matters for classical Wigner-Dyson matrices is the symmetry. But this symmetry also is important if we go beyond random matrix, classical random matrix of Wigner and Dyson, and start to consider random matrices, and not only random matrices but physical models in which there is localization. So I paid a special attention to the symmetry, and the symmetry which is usually of importance are two types of the symmetry. The first one is time reversal symmetry. And what we have shown, a bit formal, but the result is the following, that there could be two different types of the time reversal symmetry, namely the time reversal operator taken two times, so the time reversal operator squared must be proportional to a unitary matrix, because the first inverse time and then come back, it should be proportional to the unity matrix, but it appears, and it could be shown, that there are only two cases here, only two types of factors. One is with the sign plus and the other is with the sign minus. And the first type of time reversal symmetry corresponds to a simple complex conjugation of the wave function, and this is discussed in the courses of elementary quantum mechanics. But if we consider a system with a spin, then such symmetry applies to system in which the spin is integer. But if the spin is half integer, then time reversal operation is not only complex conjugation but also the spin flip. And this spin flip in the spinor space is done by the following matrix, and then if we say that time reversal operator is spin flip and complex conjugation, then time reversal squared will be -1. So there are two types of the time reversal. So there are some consequences, physical consequences of that, which we discussed. In particular, if the time reversal is like this, the Hamiltonian must be real, and real Hamiltonian has the wave function that can always be done real, and therefore if there's no periodic boundary conditions, but there are boundary conditions that does not allow current through the sample, then there will be no current also inside the sample. And this is clear, because if there is a current inside the sample, okay, if there's no current through the boundary, then the current inside the sample should be sign alternating. But yet, if we know that in some point of space current flows definite direction, this means that if we inverse time, it will be flowing in the opposite direction, and therefore, if the situation is time reversal symmetric, current cannot be there. in case of this type of density. But in case of this type of density, the orbital current is possible because there are two spin projections and they correspond to two types of the orbital current. And this can, in principle, be physically observed in so-called experiments with normal metal persistent current. So if there are some, let's say, golden rings on an insulator and magnetic flux that breaks time reversal symmetry, then in such system current may flow, and this is the result of the breaking time reversal symmetry, and this current is proportional at small breaking of time reversal symmetry. It is proportional to the flux that breaks time reversal symmetry. But it should be also, because it is a ring, it should be also proportional, it should be also periodic in the magnetic flux with the flux quantum, and so basically the current behaves like this, and this is the equilibrium current which does not lead to any dissipation, and despite this is not a superconductivity. So it was a bit controversial, but then somehow people used to believe that this is true, and this is also, it was observed in the experiment. Now, if we have time reversal such that time reversal squared is +1, then as I said, the operation of the time reversal is simply complex conjugation, and in the time reversal symmetry without the magnetic flux, there is no current. But this is not the case if the time reversal squared is -1. Then, as I said, there could be orbital current, and it must be also spin 1/2. And in this case, this persistent current is flowing at zero flux. So there is zero flux, and we may have two types of the current, clockwise and counterclockwise. And if we switch magnetic flux, so what happens is that periodicity is preserved because it is a Bomarov effect. But there are jumps at zero temperature, jumps at zero magnetic flux, jumps at magnetic flux equal to flux quantum at zero temperature. If temperature is not zero, it is of course smooth, but still with decreasing temperature one should have the slope which diverges, and in this case the slope is constant at low temperature. So this is one of the physical consequences. And then the second symmetry which we discussed was the particle-hole symmetry. And the particle-hole symmetry physically means that in such system which is particle-hole symmetric, energy level come in pairs. So if there is an energy E, then there is an energy minus E, and mathematics of that should reflect this physical requirement that eigenvalues enter in pairs. And it was long known that in superconductivity, particle-hole symmetry holds exactly independently of what is the dispersion of normal electrons, and that is because the Hamiltonian for superconducting system is a 2x2 matrix, and this time it is not a 2 by 2 matrix in spinor space, but it is 2 by 2 matrix in the space which of particles and holes, and sometimes it is called particle hole space, sometimes it is called Bogoliubov-Dijen space, because this is a Bogoliubov-Dijen operator, and sometimes it is even called Nambu space in superconducting literature. So then we repeated the same stuff which we did for spin in this case, although this is a different space. And what is the difference? The difference is that particle hole transformation involves sign minus here. This is the operator that makes particle hole transformation in the matrix space, and this is complex conjugation, this is some matrix. But important is that here there is a sign minus, and this sign minus, as I have shown, is responsible for this symmetry that if there is an energy E, then there is an energy minus E. So I'm sorry I cannot repeat twice or even 3 times the lecture, but I just say what was before. And it appears that in the time reversal symmetric case, if this Hamiltonian is time reversal symmetric, then there are also 2 cases. And one case is when time reversal symmetry operator, some reversal transformation operator, where it is +1 and the other it is -1. And when it is +1, then this superconducting order parameter, which stays here, which is a matrix in the usual matrix space, it must be odd under transposition. And then this symmetry L squared is +1. And the second case, when there is an even under transposition, and then this L squared is -1. So we have basically 3 possibilities. We have 3 possibilities with respect to time reversal. So we have time reversal squared is equal to 1, time reversal squared is equal to -1, and then we may have no time reversal whatsoever. For instance, if magnetic flux is applied and it is strong enough, then there is no time reversal symmetry whatsoever. And then there is a particle hole symmetry, and here too there is the case where particle hole symmetry twice is equal to +1, and particle hole symmetry taken twice is -1, and also there is a case where there is no particle hole symmetry whatsoever. So if we combine all this, then with each case here we may have each any of the 3 cases here, and so we have 3 by 3 9 classes out of these 3 classes of time reversal and 3 classes of particle hole. But in fact there are 10 classes and not 9. And the 10th class is the following: when there is no time, if there is no time reversal and no particle hole symmetry, there could be 2 situations. One situation is that there is no theory, there is no symmetry whatsoever. So then, okay, then it is taken into account in this when we multiply 3 by 3. But then there is another situation where there is no time reversal symmetry, there is no particle hole symmetry, but there is a symmetry with respect to their product. People who have some idea about high energy physics, they know that there are symmetries that involve the product of the basic symmetry, and this situation where there is no symmetry with respect to this, no symmetry with respect to that, but there is a symmetry with respect to their product when you do first one operation and then the other. And this gives the 10th symmetry class, and so all these 10 classes, all these 10 classes, I will give you the table, but again some important physical consequence of all this, that which was basically discovered before these 10 classes were discovered. So the history was like this. Wigner and Dyson in the 50s of last century, they discovered simple time reversal symmetry, this simple meaning two cases of time reversal symmetry and then no symmetry. And these three classes were called later on like orthogonal ensemble, where there is time reversal symmetry with t squared equal to +1. Then there is symplectic ensemble where there is time reversal symmetry with t squared is equal -1. And then there is no time reversal symmetry, which is a unitary class. And that was known since 50s last century, but then in the 90s of also last century, there was some unexpected discovery which was made by Franz Wegner and his student at that time, Renate Gade, and what they have shown is the following, that systems that can be divided by two sublattices, by actually not two sublattices but two parts. So we are now considering not only lattices like one-dimensional, two-dimensional, three-dimensional lattices, but we also consider some graphs and the localization on the graphs, because if we think of localization of interacting system, then we should consider not the real space, but the in addition to the real space, we should consider the space in which all these interacting systems are operating, so-called Hilbert space. And this Hilbert space often has structure which simplest representation is the Cayley tree. So from that perspective, now people are interested in localization on such graphs and more complicated graphs. All the graphs can be either bipartite or not bipartite. So that means that bipartite graph is such a graph that can be colored by two colors only, for example, black and white, and the connection is only between different colors, so there is no connection between the same colors. And for instance, one-dimensional system is like this, and then a Cayley tree is also like this, because we can color the first generation by white, the second generation by black, and the third generation again by white, and then connection will be only between black and white. And it appears that such structures, if they are considered like tight binding models for quantum mechanics, then you can introduce disorder to such structures, and if disorder could be two types. The first type is when the energy, when the diagonal part of the Hamiltonian, so-called on-site energy, when it is fluctuating from side to side. This is the first and the most common part of disorder that people consider in different models. But one can consider also a different type, where this on-site energy is zero or constant, and then, but disorder is in the hopping integral. So the hopping integral here, which is t, depends on the link, and on one link it is something, on the other link it is something else, and there is some distribution of this hopping. In this case, what happens to the Hamiltonian is the following: that since on-site energy is all zero, so we have zero on the diagonal. But then we have links between two sublattices, between white and black sublattices, and if I if I arrange the Hamiltonian such that there is a block of corresponding to one sublattice, then the block corresponding to the other sublattice, both two blocks are zero because there's no connection between inside one sublattice. So it is zero, and this is also zero. But there is a connection between different sublattices, and so there are two blocks of diagonal which correspond to of diagonal in a sense that this is an interaction between two sublattices. So if the matrix is of this form, then it is easy to see that it obeys the following symmetry, where sigma 3 is a generalization of the Pauli matrix, third Pauli matrix, generalization in a sense that it is a block Pauli matrix. So here it is proportional to unit matrix, and here it is proportional to minus unit matrix. Then we know that sigma 3 anti-commutes with sigma 1 and sigma 2, and sigma 1 and sigma 2 represent of diagonal terms, and because of this anti-commutation there is this sign minus. So it's what Wegener and Gadi, Renata Gadi discovered. They discovered that such symmetry is also a basic symmetry, and it is in addition to, it couldn't be reduced to Dyson symmetry, three Dyson symmetry. And that symmetry was called chiral symmetry. So then, since now we are talking about a complete set of symmetries, which are 10 classes, so these chiral classes could be, should be included in this 10. And so what I'm going to do, I'm going to again to list all these basic symmetries, time reversal with t squared equal minus 1, then the Hamiltonian is transformed in this way. So there is the block matrix of diagonal +1 - 1. This is matrix K, and the Hamiltonian must be time reversal conjugated, because each time reversal symmetry involves complex conjugation. And the symmetry like this, it means the following relation between the entries of the Hamiltonian. This is a fixed matrix, and if it is t squared is plus 1, then it is simply complex conjugation, so the Hamiltonian is real. As I said, in this case, I have shown, in this case, the Hamiltonian is so-called real quaternionic. So we have unity 2 by 2 matrix, and then we have Pauli matrices multiplied by I, and such set of 4 matrices are known as quaternions. Since this situation is always with a spin, then it involves such 2 by 2 matrices, and this symmetry means that these quaternions should be taken with real coefficients, and this is the generalization of that, where there is only a complex number, and this complex number should be real. Okay, then, as I said, there are particle hole symmetries also with +1 and -1, and the corresponding symmetry means this, where L is a certain matrix, a certain 2 by 2 matrix acting in the space, particle hole space. So I'm now fast because I already discussed all that, and we have we know what this matrix L is. So I have shown this that in this case this matrix L is like this, and in this case this matrix is like this. So everything is known what this matrix is, and then I may ask a question: how many chiral classes I can construct combining time reversal symmetry and particle hole symmetry? I said that. So in order to answer this question, you have to look only at these signs which are here, because you see, we know that the chiral symmetry is actually only present in a situation where there is a symmetry with respect to the product, T and P. So, as I said, if there's no symmetry whatsoever, no T symmetry, no P symmetry, then still there could be symmetry with respect to the product, with respect to the T times P. And this is one of the chiral symmetry classes. But, of course, if time reversal symmetry is present and particle hole symmetry is also present, then of course there is a symmetry with respect to the product. I can combine in principle each of these classes and obtain the situation which is symmetric with respect to the product. But of course there will be 4 different situations where there will be symmetry with respect to the product. But if I take, for instance, this symmetry and let's say this symmetry, then minus times minus will be plus. And since both T and P involve complex conjugation, then this H should be complex conjugated 2 times. One time when I do P transformation, and the other time when I do T transformation. So this means that if there is a symmetry with respect to Tp, then H is connected with H and not with H complex conjugated. But then this, the point is what sign will appear. If I combine, let's say, this with that, the sign will be plus. If I combine this with that, the sign will be also plus. But I need the sign minus here. And therefore, chiral symmetry classes are only when we take plus 1 and plus 1. So we have plus times minus will be minus. Or minus 1 and minus 1. Then there will be again plus times minus will be minus. And other combination, when I take let's say this and that, it will not correspond to the chiral symmetry class. It will correspond to one of these 10 classes, but not the chiral one. And also, as I said, if there's no symmetry at all, then yet could be a symmetry with respect to Tp, but this time there's no okay. So this is this 10th class, which is in some sense similar to the unitary one, because the unitary class is when there is no any symmetry. The class which is chiral unitary, this is the class where there is no time reversal, there is no particle hole, but there is Tp. Okay, and then this is the table of this zoo, which it's difficult to remember, and it is basically the collection of all what I was talking about. I simply want to show the structure of that. So first there is 3 Dyson classes. And they have some mathematical label which was known well before physicists identified these classes. It was the group theory by Cartan and the corresponding classification. Therefore, it is such weird notations. But again, this is the usual Dyson symmetry classes. So unitary class when there is no time reversal symmetry, no particle hole symmetry, and no product. Now, then there is orthogonal when there is the time reversal symmetry with plus and time reversal and symplectic where time reversal symmetry with minus. Then there are 3 chiral symmetries, and the first one, this 10th symmetry class, where there is no symmetry with time reversal, no symmetry with particle hole, but there is a symmetry with respect to DC, and it is called chiral unitary because it is least symmetric, like with the usual unitary. Least symmetric of all these. Now, then, as I said, there is plus plus and minus minus. These are also chiral symmetry, and plus plus is known as chiral orthogonal, and this is chiral symplectic. So these chiral symmetry classes or sublattice symmetry classes, they somehow is a generalization of the Dyson symmetry classes. And all these three were discovered by Wegner and Gade in 1990 or 1991. And then there are the rest 4 classes which do not belong to this and do not belong to that. And this is usually they are called superconducting symmetry classes. Here there is some typical realization of each symmetry class. Then this symmetry class has particle hole symmetry with sign plus, and this corresponds to, as I have shown, but you possibly do not remember it, I have shown that it corresponds to even superconducting order parameter with respect to transposition of this matrix. But transposition is basically permutation of two indices. But permutation of 2 indices is in superconductivity. We know that the symmetry of the order parameter could be rotational symmetry, total rotational symmetry, and then reflection of different kind, and the simplest reflection is so-called P symmetry. And this P symmetry is exactly the situation where on this random matrix language there is an even order parameter is even with respect to transposition, and this corresponds to time reversal symmetry taken twice equal to 1, and this is P wave order parameter. Then there could be -1, and this, as I said, corresponds to completely to even order parameter with respect to transposition in this matrix, and this corresponds to so-called singlet state by singlet, because altogether there should be spin degrees of freedom and orbital degrees of freedom. They should be even, because these are 2 fermions. If I change the permute the particle, then the wave function should acquire sign minus, so altogether it is even, altogether spin degrees and orbital degrees, altogether they should be odd by permutation, because it is 1/2 fermions which are permuted, and then the situation where the orbital part is symmetric in this context under symmetric, because -1 here corresponds to +1. -1 there corresponds to +1 here, and this is a single pairing, and this is the most common type of superconductor. Then when appears also non-trivial time reversal symmetry, it is always the business of spin-orbit interaction in this case and also in this case. and then, okay, so this, what you should remember is that there is three classes of usual dice, and then three classes of which are chiral classes with different symmetry with respect to transformation of the Hamiltonian, and then four classes which are related with various superconducting cases. That is it. So, yeah. So I'm sorry for this Zohar, but the thing is that after these 10 classes were discovered, they are always cited in the literature, and so if you first see symbols like that, so you are scared. Tartan group, what it is, I don't know. And in fact, everything is pretty much elementary, but of course you have to have this table in the pocket, and your poor brain, if it is not a mathematician brain, cannot remember all these things. But what physicists could do, physicists could understand that where it is from, and what is time reversal symmetry. It is, everyone can imagine. What is particle hole symmetry? It is also a very clear physical statement that that all the eigenvalues enter in pairs. And then you understand that there is such a Zohar, that it is not something which is, is not possible to understand. It is possibly not possible to remember, but you can go and see this table, and then you feel more comfortable in all this stuff. So that's why I have been talking about that. And then, of course, each symmetry has physical implication, as I said. Yeah.
No, it was exactly the question about the physical implications. For example, do I understand correctly that you mentioned that this symmetry is broken by a strong enough magnetic field? So, for example, how can I think of it in terms of real physical systems? Is, for example, I have a superconductor, right? And I start to apply magnetic field, and until the magnetic field is small enough, the superconductivity is preserved, and I still have a T-symmetry, right? So when I have like more regular superconducting transition, that means that I have strong enough magnetic fields, and that means that I go from the class with time reversal symmetry to the
you are
class.
right.
Okay.
You are right, absolutely. Mm-hmm. So you see, there are these clean classes, so the symmetry classes. Okay. But then, of course, you may apply some symmetry breaking factor, like magnetic field, for instance. And this symmetry breaking factor makes your Hamiltonian not exactly symmetric with respect to anything, and it doesn't belong to any of these classes. Mm-hmm. But if the breaking of the clean class is weak, then you have a situation of so-called crossover from one class to the other, where basically what means crossover? Crossover means that there is a mixture of the properties of one symmetry class and the other. But when the symmetry breaking factor becomes very strong, then you come to the situation like this. So, for instance, suppose you have an orthogonal case, and the orthogonal case is a real Hamiltonian. So the real Hamiltonian, as I said, it doesn't allow for current if it is not a periodic boundary condition. But if you add magnetic flux, then you break this orthogonal symmetry, you break this type of time reversal symmetry, current appears. But until this flux is not very strong, you are in a mixed situation. But when it becomes very strong, it completely breaks any any signature of the time reversal symmetry, and then you are in a unitary situation.
Another question: is it always? You mentioned that there is like a crossover, right?
Yeah.
But is it like in real physical system? Is it an actual crossover, or is it correspond to some kind of phase transition where?
No, it is a crossover.
Always.
It is to the best of my knowledge.
Okay.
Never say never, but to the best of my knowledge, it is always a crossover.
Okay.
Okay. So this is all about the symmetry classes, and now we come to more traditional thing. And so in one of the first lectures, what I have shown, I'm repeating because many people were not there. In one of the first lectures, I have shown the following, that Wigner-Dyson's random matrices are defined as matrices such that they are symmetric under basis rotation, and this leads to decoupling between statistics of eigenfunctions and statistics of eigenvalues. And I have shown how does it happen. So I have shown that so this is the form of this invariance under changing of the basis, because here stands this is the probability of entries, this is the measure, and here there is always a trace, and when I change the basis, these matrices U and U dagger appear on the left and on the right, but because of the trace I can make a cyclic permutation and these matrices disappear, and what I get the simple trace of the eigenvalues if I say that H is parameterized through the set of eigenvalues and the set and the matrix is made of eigenvectors, unitary matrices made of eigenvectors. So then when I simply plug it into here, I get this stuff, but this is not all, because I made a transformation which is similar to the transformation transformation from Cartesian variables to polar variables, and then one has to compute the Jacobian, and when this Jacobian in principle is computed in the same way as we do it for the polar coordinates, and the result is that this Jacobian is very non-trivial. This Jacobian is a product of the modulus of difference in different eigenvalues for the orthogonal ensemble, where the Hamiltonian is real, and this is denoted by beta equal 1 because here stands 1. Then if there's no any symmetry in the three Dyson classes, then it is called, then H is complex and a complex emission matrix, and then this Jacobian acquires a square here. But if you are in a symplectic case where there are, in this case, the Hamiltonian is described by one real number. I mean, any entry is described by one real number. In this case, any entry is described by two real numbers, real part and imaginary part. And then there is also a symplectic case where it is time reversal symmetry squared is -1, and there is a spin degrees of freedom. And then, as I said, any entry can be represented as quaternions, and these quaternions are 2 by 2 unity matrix, and then I sigma I, where I is equal 1, 2, and 3. And this is for matrices. And the symmetry, time reversal symmetry with t squared is equal to -1 tells you, and we have shown that any entry H and M, which in this case is 2 by 2 matrix because of the spin 1/2, it is some H0 and M, one real number, plus I H1 and M, another real number, times sigma 1, and then the same with sigma 2, and the same with sigma 3. So we have four numbers, four real numbers that describe any entry, and because of that, here the power 4 appears, and this is the most trivial part, most non-trivial part of this big Dyson theory is this Jacobian. Now, now I take this Jacobian together with this part where I simply which arises from exponential of minus trace h squared, and I put here any beta 1, 2, or 4 which arises from symmetry, and then I just rewrite it in the following way. I rewrite it like the classical statistics where there is exponential minus beta, which is inverse temperature, and then some energy function. So the usual system, usual system is described by such distribution where there is inverse temperature and some energy function. And if I compare this and that, I will find that this energy functional is like this. It is simply the energy in some parabolic potential. And the analogy here is the following. So the energy levels of the matrices are considered like a coordinates of a particle in one dimension. And then if I have n particles in a parabolic potential, and these particles do not interact, then I would have the energy which is the sum of the energies in this parabolic potential. And this will be this part. But then there is this part which which contains two energies or two coordinates of particles in this analogy, and this is interaction. So interaction of a very special type, because it is very long range. It is a logarithmic repulsion. So if the distance is small, then the logarithm is negative, and we have a positive energy, which means repulsion. So this is a logarithmic repulsion, and this is non-interacting energy of non-interacting particles with coordinates En. So then what we see the following, that the statistics of energy levels in the Dyson ensembles, they correspond to statistics of classical particles, and these classical particles interact with, repel each other with logarithmic interaction. And this is the consequence of the calculation. So we took distribution of the entries of matrices, then we made a transformation to eigenvectors and eigenvalues, then we obtained that eigenvectors and eigenvalues are decoupled, and the distribution of eigenvalues has a non-trivial part which comes from the Jacobian, and this Jacobian is then interpreted in this analogy with classical particles like a logarithmic interaction. So then the thing is that the logarithmic interaction of particles is actually an element of many exactly solvable theories. So, for instance, vortices in superconducting, in two-dimensional superconductivity. Vortices in two-dimensional superconductivity, they also interact via logarithmic interaction, and because of that, a very peculiar phase transition appears, which is the Kosteles-Tauris phase transition. So this model of classical particles with logarithmic interaction, it is sort of a signature of exact solubility. So this is the particular mathematics that is used for this exact solubility, to obtain the exact solution, is different in different models, but they are all very much connected with each other. So this is a very famous interaction. Now what one can do, one can rewrite this functional in a continuous way.
I'm sorry. Shouldn't be there like 1 over beta in front of the first term?
Look, this does not matter for the following reason, of course, but this doesn't matter, I tell you why. The thing is that I can change the units in which I measure energy. Okay.
Oh, okay.
When I change the units in which I measure energy, I change this parameter.
Yes.
I can always put it at 1. And then what happens here if I change the scale of the energy is that here there will be some factor, logarithm of these factors is an additional constant, and energy is always defined up to the constant. Therefore, I don't want to keep unnecessary parameters here. Now, of course, this thing I can rewrite in a continuous way, but this is, for the moment, it is an exact transformation. I introduced the density of levels like this, and then I plug it into here. If you plug it into here and make integration, you will obtain exactly this form. Why 1/2? 1/2 is because here I did not type it till the end. It should be n greater than m here, and therefore here there is 1/2. Now, why did I write it in this form? It is for the following reason. We will use this form later on to get some properties of, for instance, semicircle is most easily proven in this way. So what you do, you do the following. When I plug it, this form into here, I exactly get this expression. But I can do, I can get this expression and then say, you see, this thing is a set of delta function, right? And then it is an exact expression. But if I say that I smoothen this this path so that this rho is a continuous function and not the set of spikes, then this will be an energy that depends on the continuous variable. When it is good to do? It is good to do when you are interested in the energy scales, in the behavior of something at the scale which is much greater than the spacing between the levels. So the spacing between the levels, it is inversely proportional usually to some power of the size of matrix. And when size of matrix goes to infinity, then any width to this delta function. So if I change delta function, let's say by Lorentzian with some width, and then send size to infinity, then I will get the continuous approximation. And for things like computing asymptotics at energy difference much bigger than the mean-level spacing, such continuous approximation is good, and I will show what will it result to. So basically this is in some sense the rewriting what I have done already when I derived the joint probability distribution of energy levels, but it is a useful rewriting because we have some intuition about what is happening to classical particles when they repel each other. And we cannot say exactly what is the effect of logarithmic repulsion without calculation, but some qualitative features we may keep in mind. For instance, if you look at this energy, you will see that the particles, this is not a plasma like in Kosterlitz-Tauris case, where there are vortices and anti-vortices. Here there are only the sign of interaction is always the same. So it is like particles which interact with each other at any distance, and interaction slowly decreases, but it is always positive. This is always repulsion. So what happens to such particles if we take such system of many particles like this? Of course they will flow away, because they repel each other, they go to infinity. So this statement is our intuition about what happens to interacting classical particles if they all repel each other. So we immediately see that such system is not stable. In order to stabilize this system, we have somehow to restrict this expansion. And one way to restrict the expansion is to put this parabolic potential, because if you take repelling particles in the parabolic potential, they do not go to infinity because it costs too much of the energy to go to infinity. Having this term, we stabilize the system, and therefore this thing is known as confining potential. Okay, because it confines the system, doesn't let it go to infinity. Now, as I told you, the initial distribution of the matrix elements, P of H, it can be written like exponential of minus trace. Classical diagonalization is trace H squared. But in principle, the fact that eigenvalues and eigenvectors will decouple, it is only because of this trace. It is only because trace of u h squared u dagger is equal to trace h squared. But if you write here not h squared, but let's say h4 or something or some other function v of h, which can be expressed, which can be expanded like a1 h squared hk h2k, for instance, then the same thing will happen. So you will have decoupling between eigenvalues and eigenvectors. But the confinement potential will be not e squared like here, but will be something will be v of t. This v which stands here. So this can be generalized by writing some confinement potential here, which makes the goal of confinement, but this confinement could be steep or it could be shallow, and we will see what will happen. So in this continuous description, I have written arbitrary confinement potential. So for this model, I should have written e squared, but in principle, I can consider basis rotation in invariant systems where here stands some arbitrary v of e, and I put it there. Okay, so this is the classical analogy. So in addition to the classical analogy for the matrix eigenvalues, there is other much more sophisticated analogy which is quantum. And now I want to tell you something about this quantum analogy. So the idea is all the same. So we find the distribution of eigenvalues for Wigner-Dyson matrices. It is like this. And there is a mathematical object which is very popular and has many nice properties, and it is called Vandermonde determinant. So what is Vandermonde determinant? It is the determinant of matrix like this. So the first row is unity, the second row is E1, E2, and so on, En. And then square, and then the third power, and in the end, n minus 1 power. And this is the n by n matrix. So the first property of this determinant is that one can show that this determinant is exactly I mean, not this. The first property is the following: that this determinant. I did not make this slide. Okay, I did. Let's take this next slide. Okay, so this determinant actually. Okay, I will not confuse you. I just say that you see, if I permute two columns of any determinant, I will change sign of the determinant, right? On the other hand, this permutation means permutation of 1 and 2, and 1 and something else. So I permute two particles. I permute the coordinates of particles. So, for instance, I make 2 equal 1 and 1 equal 2. And that changed the sign of the determinant. So then, if you look more precisely at this determinant, you will see that the first property is that it changes sign when I permute any two coordinates of particles. I mean, I just permute two particles. This is the first property. And the second property is that that this determinant is the sum of such difference to the first power. So, for instance, if we take this determinant as of the size 2 by 2 matrix, so we have determinant E2 minus E1, right? So if you take 3 by 3, you take the product E2 minus E1, E3 minus E2, right? And then by induction you can prove this thing. And therefore, this Jacobian, which is equal to this product, it is simply expressible in terms of this determinant as the modulus of the determinant to the power d. So, of course, this thing does not change sign because it is already, the Jacobian must be positive. But there is an object that does change sign, and the Jacobian is expressible through it. Now why I'm talking about that? Because if you have a quantum problem, quantum particles in one dimension, and if those particles are fermions, then the wave function must be antisymmetric with respect to permutation of 2. And this guy is exactly of such property. So if I permute two particles, I change the sign. So this guy is a candidate for the wave function of fermions, because it changed sign by.
But I mean, we want some probabilistic interpretation from the wave function, right? And here it is just artificially made.
Wait a bit, I will
Okay.
show. So the only thing I want to say that this thing, this van der Monde determinant is the candidate for the wave function of fermions because it changes sign by permutation of two particles. Now we go further and compute things like that. What is it? It is simply the momentum, the total momentum, the second derivative with respect to coordinate is what? Is minus p squared, right? Where p is momentum operator. Therefore, this is the action of minus p squared to such a wave function, right? What is minus p squared? The sum of all particles minus p squared. It is kinetic energy, right? Now, so the third property of this object, of this mathematical object, is the following. It is necessary to prove all these properties, of course, but I don't have so much time to prove it all. You can try yourself, and this would be an excellent problem. But all what I want to say that this is an action of minus p squared on the wave function. And the property of this object is that this sum is equal to 0.
Is the first derivative of this determinant is also 0 with respect to energies or not? I mean, you state that the second derivative over energies.
Yes.
Sum.
This is not energies. This is the coordinate of the particle.
The parameter. Sum over them is 0. So is the same properties holds for the first derivative or not?
No.
Okay.
No. So the first derivative is more complicated, and the second derivative is like this. So this means that the total kinetic energy is equal to 0, if I say that this is a wave function. So when the total kinetic energy is equal to 0, this is the ground state of fermions, right? If they have vanishing density, then it is the ground state of them. Okay. So this identity is a hint that this is not only the wave function of fermions, but this is the wave function of free fermions with vanishing density and the ground state of it. Okay. So I'm just increasing complexity. So this is to prove this identity from here is next level of complexity, and then let us do even more. So the next identity is the following. Let me include the confinement potential. So now it is not a vanishing density. So the first thing these particles went away because they repel each other. They went away. Yeah, there was no confinement potential. But in order to make this to regularize this problem, I I consider things like that. So this van der Monde determinant, but multiplied by such factor, and then again the second derivative. This is an arbitrary parameter, and one can show that this van der Monde determinant has a property that this thing is proportional to itself. So when I apply this second derivative and sum, then I will get something multiplied by the same thing. So this means the following, that if I have some Hamiltonian and the wave function, so I multiply this, I apply this Hamiltonian to the wave function. What I should get the energy of this state multiplied by this function, plus possibly some potential energy, because if I this is kinetic energy, but if I subtract this term from here, then I get. This is minus kinetic energy. So if I put here with a sign minus, then there will be minus kinetic minus potential. So there will be some Hamiltonian with quadratic potential. And the identity tells you that this van der Monde determinant is indeed a solution of the Schrödinger equation, in which there is a kinetic energy and then there is also a potential energy. And this time, of course, there will be some energy of the ground state, which is not zero, because there is a confinement potential. It holds this system and makes a finite density.
How to express this energy of the state through known En or any other parameters?
You mean this thing?
Yeah.
It's a cumbersome equation. You can express it, but it is a cumbersome expression which I did not write down here because it is it doesn't add.
But it doesn't involve.
No, I mean
M, right?
you can compare it with what it should be. I mean it is the ground state energy of such system, we know, right? If it is non-interacting.
But it is a function only En, right? Not M.
It's function of the total number of particles. So, the ground energy in the confinement potential. So you find the spectrum, and then you fill in this spectrum like a Fermi sea. And this is simply the energy of the corresponding level. So the problem of fermions in quadratic potential, and I'm sorry I did not write it down. It is a cumbersome expression. Okay. So what we see the following, that indeed, if I take the van der Monde determinant, it will be the solution of the Schrödinger equation for fermions. Why for fermions? Because it is antisymmetric. It is a many-body wave function for fermions in a confinement potential, together, of course, with this factor. And so, since there is only confinement potential, so interaction of the particle with a potential and not interaction with each other, because there is only one body term here, then we see that this system of energy levels, so the van der Monde determinant is multiplied by this factor is a wave function of free fermions, because there's no potential energy is only one body energy, the energy in the of one particle in the potential. So now what we can do, we can find the square modulus of this wave function, and we find the square modulus of this wave function, and what we see that there will be for beta equal 2, I will get exactly this Jacobian, and then and then this part will be exactly sorry. Okay, and this part will be this part, one body part, one confinement potential part of the distribution. So what I have shown, not proven, but I told you which identity should be proven for that. So I have shown that that this on one hand is the many-body wave function of non-interacting electrons in quadratic potential. On the other hand, if I take square modulus of that, I will get the density, quantum mechanical density of such particles. Okay, and this quantum mechanical density of these particles will be the joint probability distribution of energy levels for Wigner-Dyson matrices. So this is the quantum analysis. So if beta is equal to 2, you may say that the joint probability distribution of eigenvalues can be considered as psi modulus square of many-body wave function for fermions, non-interacting fermions, in the confinement potential. So this is the analogy in the simplest case. But what to do if beta is not equal to 2? What to do in this case? In this case, we do the following. We just find what is the Hamiltonian to which this wave function is a ground state, or it is simply first that it is a solution of the Schrödinger equation. So why this? Because if I take the modulus and put it to the beta power, then the modulus square and put it to the beta power. Just take the modulus square. So just take the modulus square. If I take the modulus square, I will get this en minus en to the power beta, like in the joint probability distribution of levels. And this guy will be unity when I take the modulus and raise it to square. So if this if I find which Hamiltonian this function is a ground state, then I find the analogy for the case beta is not equal to 2. So, you see, this is in some sense an inverse problem. Instead of solving Schrödinger equation, I find this the Schrödinger equation. I find what is the interaction. So, so what I should do, I should take the kinetic energy, which is the sum of second derivative with respect to E. And as you remember, when this was simply the van der Monde determinant, then the second derivative was 0. And this indeed corresponds to the case beta equal 2. When beta is not equal to, I just take this, differentiate as it should be. So it is simply a simple problem. And what I find this. I find that the sum of the second derivative of this wave function will be again proportional to this wave function, to this one. But here there will be something. There will be this factor, then there will be van der Monde determinant, and then the sum of the second derivatives of the van der Monde determinant. So it is quite a complex thing after I made differentiation. You can check it. But then, when I look at that, I can say, well, here I did not put confinement potential for simplicity. So it is like the first row without this confinement potential. So what I can say the following, that this is a minus kinetic energy, and this part is interaction. And so let us see what this interaction is. Okay, so this is just, I have rewritten what I obtained by taking the sum of the second derivative. And now, again, some nice property of van der Monde determinant. So, if I take the sum of squared of the first derivative, it appears to be things like this. And so when I put this guy into here, I obtain finally the Hamiltonian for which this wave function is a solution. And this Hamiltonian appears to have kinetic energy, of course, and then a very celebrated interaction, because this inverse square root interaction, it is called Calogero-Sutherland model. So there are several Calogero-Sutherland models, but all of them share the property that this is an inverse square interaction.
Sorry, in the second line on the right, yes, but on the right, that it should be sum over n and m more than n, right?
This is a sum over n and m. Sorry.
Okay, yes.
I mean, it is.
Okay. Thank you.
Of course. So, when writing such formulas, you always have problems. Okay, so what you see, you see an extremely nice property that even if beta is not 2, so for beta equal to, this interaction disappears. And this is a real interaction. So as I said, I did not insert here the confinement potential in order not to make it very cumbersome. But this is a real interaction. It depends on the coordinates of two particles, a two-body interaction. And it is present when beta is not equal to 2. And this is the Hamiltonian such that the wave function, the wave function like this is a solution to that Hamiltonian. It is constructed in the symbol. And then, as I said, if I take square modulus of that, I exactly obtain the joint probability distribution without confinement potential because I didn't include it. Okay, then this is basically all what I wanted to say for today. I only just invite you to enjoy the all these identities valid for van der Waals determinant, which has some physical implications that we know what kind of many-body system, the solution is the many-body fermions, and the solution is corresponds to joint probability distribution of energy levels. Okay, the only thing that where I cheated you is the following: that I have shown that this thing that this thing is the solution to such many-body equation. I did not show that this is a ground state. So I didn't show that this is a ground state. I did not find a way to show it very, in a very simple way. But we will see later on that indeed this is a ground state. In order to show that, I will have to tell you what is the Latinger liquid formalism for interacting particles, and then you will see that it is indeed corresponding to ground state or to zero temperature. The idea is the following: that when I consider correlation functions of level densities, then it appears that these correlation functions are decreasing as a power law. And any correlation function for finite temperature decrease exponentially, and only the ground state decrease as a power law. And we will show that this for Wigner-Dyson case it is a ground state, and it is a power law, and then it will automatically mean that it is a ground state. So this is the physical way of justifying that this is the ground state. Okay, so the thing is that I'm trying to tell you see things which are from different corners of theoretical physics, because there is random matrix theory, there is exactly solvable models like Kalodger-Sutherland, which are solved by data ansatz and things like that. And this is a specialization, I would say. And then there are things like Latinger liquid people, which it's a whole piece of condensed matter theory. I'm trying to combine it together. Of course, this is not possible within the time I have to prove everything. But this is not even needed, because the thing is that if someone is interested, he could go into detail. But I hope that some incomplete presentation of this nevertheless gives you a flavor of the analogy, of the classical analogy, which is simple, and of this quantum analogy, which is not at all simple, because this is very complicated. By the way, this is the last thing. By the way, people who did beta ansatz solution and things like that, so they take this Hamiltonian as a given thing and try to solve it for any values of beta. The analogy that I have shown, it is only for beta is 1, 2, and 4. In this case, it is analogous to random matrix theory, and the solution from random matrix theory is much more simple than the one by beta ansatz. And then the question arises, is it possible to generalize the Wigner-Dyson, maybe taking different matrices such that that this beta is arbitrary? What was known for the beta ansatz when people solved this, irrespective of the random matrix theory, they have found that if beta is not equal 1, 2, and 4, then there is an extremely uneven dependence on the beta. So there are jumps, very complicated structure. And only for this beta 1, 2, and 4, things simplify. And so this is relatively recent stuff. For instance, who is interested could read paper by Dima Gangard, who was also involved in that. But the thing, why I'm saying about that, because it is really an analogy, but an analogy such that this model is much more complicated than random matrix theory when beta is not equal to these famous numbers 1, 2, and 4. Okay, and then the last slide. This is simply the summary. So if I take such a wave function, then it will be the solution of the Schrödinger equation, many-body Schrödinger equation with such Hamiltonian, and the density psi squared is the distribution joint probability distribution of the energies. But it is related with very, very non-trivial quantum mechanical Hamiltonian, so one can say, well, if it is so non-trivial for beta is not equal 1, 2, and 4, what is the reason we make this analogy, because solution of random matrix theory is much simpler than the solution of that. The reason will be seen when we go to correlation function at large distances between the energies. For instance, density correlation function in at large energies, and there is a certain machinery which allows, starting from here, then to derive a simple asymptotic Hamiltonian for this model, and then solving it, you can say what will be the asymptotics for the correlation functions, and then you can consider arbitrary b because arbitrary beta because for large distances all this irregularity does not play much role, and what we will see that if we will see that first of all that Wigner Dyson corresponds to the ground state of that, and second, we could go beyond the ground states. We could consider this model for this beta equal 1, 2, and 4, but not for the ground states, rather for the final temperature. And that appears to be related with random matrices, which I have shown to you in the introduction. Okay, in the introduction, I have been talking about matrices which are Gaussian, but with variance that depends on the distance from the diagonal, and then there is some critical case where this A is equal to 1, and it appears that this critical case is described by the Kalogero-Sutherland, but not the ground state, rather the Kalogero-Sutherland solution not solutions, but correlation functions at finite temperature. And this is the reason why I went to describe you this complicated quantum analogy, because then it allows to say what will happen not in the Wigner-Dyson case where we know everything, rather than in the case of power low-banded matrices in which there is no decoupling between eigenvalues, eigenvectors, there is no this rotation invariance, and yet using this analogy we can say something.
No, it is time.
Okay.
Yeah, I just.
So I'm sorry, maybe it is a bit too heavy, but I just wanted you to give some